Dear all, a very good day. In the previous lecture, we have discussed about some of the very important voltages that are a part of the VTC, that is voltage transfer characteristic of an inverter. And the important voltages that we had observed were VOH, VIH, VIL, and VOL. Okay, now all these voltage levels are defined. Among these, VIH and VIL are very important as they dictate what is the amount of noise that a system can allow to pass through it. Therefore, in the present topic, we are going to discuss noise immunity and noise margin. Okay, now to observe the effect of noise on the system, okay, or to observe the noise on the circuit reliability, we will consider a circuit consisting of three cascaded inverters as shown here. Okay, these inverters are connected back to back, and we are assuming that all three inverters are identical to each other. Okay, and then we will consider the different voltages which we are applying at these inverters and see what is the effect of noise in these inverters due to interconnects or any other reason for which it may occur. Okay, so for the discussion purpose, we have assumed that the input of first inverter is VOH, that is output high. Okay, therefore by the definition, the output voltage of the first inverter will be equal to VOL. So if we are giving a VOH as input, that is output high as an input, so its output level should be VOL. Okay, now this signal is this VOL needs to enter the second inverter so that we can get an output from the second inverter. But due to the interconnects, there may be effect of noise. Okay, so now this output signal is being transmitted to the next inverted output by interconnect, which could be metal or a polysilicon line connecting the two gates. Since on-chip interconnects are prone to signal noise, the output signal level of the first inverter will be reduced during transmission. So because of this interconnect, this output level of the first inverter can get affected. Okay, so consequently, the voltage level of the input of second inverter will be either larger or smaller than VOL. So we are showing here that input is VIL. This input VIL can be either greater than or less than this voltage. Okay, due to the impact of the noise which is flowing here. So if the input voltage level, because it is output low, so here input should also be low, and it should be low enough to be considered as logic 0. So if the input voltage of the second inverter, now this is the second inverter, its input voltage, okay, is smaller than VOL, this signal will be interpreted as logic 0. So if this VIL is smaller than VOL or even equal to it, so it will be considered as logic 0 here, and this signal will be interpreted correctly as logic 0 by the second inverter, and the inverter can correctly assume that this inverter will correctly assume it as logic 0. However, if this voltage becomes higher than VOL, okay, or we can say it becomes higher than VIL, VIL is the level which is considered low for this inverter. Okay, then because of the noise, this inverter will not function properly. So on the other hand, if the input voltage becomes larger than VIL, as a result, the noise, then it will not be considered or interpreted correctly by the inverter. Thus we conclude that therefore we can finally say that VIL is the maximum allowable voltage of the voltage at the input of the second inverter, which is low enough to ensure that its output will be logic 1. Okay, so in a very layman's language, we have applied 1 here, output should be 0. Now this zero output is going to the second inverter. Okay, now if the voltage of this voltage level of due to this noise is greater than VIL, then this output cannot be considered as logic 0 and it will not be VOH here and it will not be correctly understood. Therefore, whatever the output is here, the impact of noise should reduce it below VOL, but it should not be higher than VIL. Then only we can get a satisfactory VOH here. Now we will consider that the signal is transmitted from the output of the second inverter to the input of the third inverter. Okay, now we are focusing in this region where this output high is connected to the input of third inverter. Okay, so assuming that second inverter produces an output level of VOH. So we have assumed that this is correct. We have we received a logic 0, therefore logic 1 is here, and the voltage produced corresponding to logic 1 is VOH by the second inverter. So this output signal will be perturbed because of the noise interference. Now again there are interconnects, and because of the interconnects there is a noise, and due to which this signal will be affected. Okay, so this output signal will be perturbed because of the noise interference and the voltage level of the input of the third inverter circuit, and it will be different from VOH. So its value will be lower or higher than VOH. Now if the input voltage of the third inverter is larger than VOH, this signal will be interpreted correctly as logic 1. So when this is being applied as an input to this, we need that this should get a logic 1. So this will be understood as logic 1 if the value due to noise is increased or it is becoming higher than VOH. Okay. However, if the voltage level drops below VOH, so if this voltage level drops below VIH, okay, due to noise, if this voltage level falls below VIH, then it will not be considered as logic 1 and it will be considered as logic 0, and we will get a wrong output. Therefore, due to noise, we do not want that this signal level here falls below the level of VIH. Okay, so consequently VIH is the minimum allowable voltage at the input of third inverter, which is high enough to ensure logic 0 at the output. Now these observations that we have just discussed, okay, lead us to the definition of noise tolerance for a digital circuit, and this is known as noise margin. Okay, and it is denoted by Nm. The noise immunity of the circuit increases with Nm. Okay, if we have got a good noise margin, that it means circuit is not easily affected by the noise. Now for our practical purposes, there are two noise margins that are defined, and these are NML, noise margin low, for low signal values, and then other one is NMH, noise margin high, for high signal values. Okay, these are defined as NML is equal to VIL minus VOH and NMH is equal to VOH minus VIH. This will be much better understood if we will focus on this circuit. Here we have shown the input voltage levels with VIH, maximum input, VIL and minimum input, and here is the output levels. Okay, so NML is this shown here. It is the difference of highest input level, which is considered logic 1, and VOL. So as long as these there is a good difference, so this is the noise immunity which is acceptable in the circuit. In the same time, if we are looking at NMH, noise margin high, then VOH and VIH are here, so it will be VOH minus VIH. Okay, this is again a confusing part because students don't know where to put input first and output first. So if you will remember just this figure, you will be easily it will be easier for you to remember how the calculation of different noise margin occurs. Okay, this is a graphical representation, and shaded areas indicate the valid regions of input and output. Yes, So this is the valid input, this is also valid input, this is the valid output, and this is the valid output. Any variation in this will result in change in the noise margin conditions. Okay. So this is for this present lecture. Thank you. For the next, we will be looking at power and area consideration, or possibly at a resistive load inverter circuit. Thank you.